Imagine you are standing in a room. The walls are metal and polymer. The air inside is warm, carefully pressurized, carefully filtered. You can breathe. You can hear the soft hum of machinery. Outside those walls, just beyond a shell, perhaps a few centimeters thick, the temperature has swung 200 degrees in the last hour. A fine powder coats every surface, powder so sharp it can sever individual cells in your lung tissue. Invisible particles rain down from the sky without pause, silently rewriting the DNA of anyone in their path. The nearest mechanic, the nearest hospital, the nearest backup of anything you need is 250,000 miles away. And in this room, you are not visiting, you live here. And the environment is trying, patiently and systematically, to kill you. On May 26, 2026, NASA awarded its first construction contracts for a permanent moon base. Not a temporary outpost, not a flags and footprints mission. A place where human beings would live and work continuously on the lunar surface for months, eventually years. $20 billion committed, a decade-long construction timeline. The animations look extraordinary, but almost nobody is asking the harder question. Not whether we can build a structure there, but what happens after it lands? What happens when you try to keep it working? What happens to the people inside, not for a week, but continuously, across months and years, in an environment that attacks every material, every seal, every machine, every biological system, every day, without pause? That question changes everything, and the answer is far worse than you think. If questions like this make your mind catch fire, subscribe. We go deeper every single week. On March 24th, 2026, NASA held a press event it called Ignition. The agency announced a complete restructuring of its Artemis program around a single, long-deferred ambition, a permanent base on the surface of the moon, not a short sortie camp. A phased, continuously expanding installation near the lunar South Pole, designed to support human beings living and working on another world for months, eventually years at a time. Administrator Jared Zachman framed it in language that left no ambiguity. America would never again give up the moon. Within weeks, contracts flowed. Blue Origin would provide the Mark I Endurance lander, targeted for no earlier than fall 2026. Astrolab and Lunar Outpost would build the rovers. Firefly would handle orbital relay infrastructure. NASA unveiled not a single habitat module sitting alone in a crater, but a distributed network of assets spanning hundreds of square miles. Habitats, science stations, power units, roads, communication relays, rover garages, and autonomous hopping drones called Moonfall that could scout terrain on their own. The scale was not modest. It was the most ambitious surface infrastructure plan NASA had announced since the Apollo program. The momentum felt real. Just weeks earlier, Artemis II had completed its mission, 4 astronauts flying around the moon and returning safely, validating the Orion spacecraft and the deep space life support systems that would underpin everything forward. Artemis III was restructured as an orbital docking test in 2027. Artemis IV, planned for 2028, would attempt the first crewed lunar landing since 1972. After that, crews would land every 6 months, building capability with each visit until the base could support continuous occupation. The coverage was enthusiastic. Social media imagined pizza restaurants on the moon. The narrative was clear. Humanity was going back, and this time we were staying. Almost nobody paused to ask the harder question. Not whether we could land on the moon again, we clearly could. Not whether we could build a structure there, engineering firms were already designing them. The harder question was what happens after the structure lands? What happens when you try to keep it functioning for years in an environment that attacks every material, every seal, every machine, every biological system, every single day, without pause? That question is where the real story lives, and the answer begins with what the moon actually is as an engineering environment. The lunar surface has no atmosphere. That sentence gets said so often it has lost its power. People hear it and picture an airless landscape, maybe a little dramatic, but manageable. That reaction misses almost everything. No atmosphere means no air pressure. Every habitat on the moon is a pressure vessel, an inflated structure holding breathable air against the vacuum of space. If the wall of your house on Earth develops a small crack, you get a draft. If the wall of your habitat on the moon develops a small crack, you get explosive decompression. There is no margin, no forgiveness. Every seal, every joint, every window, every airlock mechanism is a potential point of catastrophic failure, and every one of those components sits under constant mechanical stress from the pressure differential between inside and outside every second of every day for as long as the base exists. No atmosphere also means no thermal buffer. On Earth, the air around you carries warmth from sunlit areas to shaded ones, moderates solar input, stores and releases thermal energy. None of that exists on the Moon. Heat can only travel by radiation and conduction, no convection, no insulating blanket of gas to soften the temperature swings. At the lunar equator, surface temperatures range from roughly 127 degrees Celsius in direct sunlight to minus 173 during the lunar night, a spread of 300 degrees cycling every 29.5 Earth days. At the South Pole, the situation is different but not easier. Even the best illuminated ridge sites experience periodic shadow, and in the permanently shadowed crater floors where the precious water ice waits, temperatures plunge below minus 200 degrees. Some measurements place them below minus 230, among the coldest naturally occurring temperatures anywhere in the inner solar system. No atmosphere also means no protection from radiation. On Earth, the atmosphere provides shielding equivalent to roughly 10 meters of water above your head, and the planet's magnetic field deflects most incoming charged particles before they even reach that layer. The Moon has no magnetic field worth measuring, and no atmosphere worth mentioning. Every particle of galactic cosmic radiation, every proton and heavy ion accelerated to near light speed by distant supernovae, arrives at the lunar surface with its full energy intact. Solar particle events, sudden bursts of energetic protons ejected during solar flares, hit the surface unimpeded. China's Chang'e 4 lander provided the first direct radiation measurements from the lunar surface, recording an absorbed dose rate roughly 2 to 3 times higher than what astronauts experience aboard the International Space Station. On the unshielded lunar surface, a human being accumulates approximately 400 millisieverts of radiation per year from galactic cosmic rays alone. NASA's career dose limit for astronauts is 600 millisieverts total. A single large solar particle event could deliver a lethal dose in hours. NASA chose the South Pole for good reasons. Crater rims near Shackleton and other polar formations receive near-continuous illumination for much of the lunar year, the best solar power conditions available anywhere on the Moon, while nearby permanently shadowed craters contain water ice that has been accumulating for billions of years, shielded from sunlight by crater walls that never see the sun. The proximity of power and water in the same geographic region makes the South Pole the only viable site for a permanent base at current technology levels. But the South Pole also introduces constraints the press conferences rarely emphasize. The sun never rises more than a few degrees above the horizon, casting long shadows that shift slowly as the Moon rotates. Communication with Earth is complicated by the low sun angle. At the South Pole, Earth hangs very low on the northern horizon, and local terrain frequently blocks the line of sight between a surface antenna and Earth. The base cannot rely on a single fixed antenna the way the ISS relies on its direct link through relay satellites. It needs orbital relay infrastructure, either satellites in lunar orbit or communication towers placed on elevated terrain, each one an additional system that can fail, cost money, and require replacement when its operational life expires. The sites where illumination, stable footing, acceptable slope angles, communication line of sight, and proximity to shadowed ice deposits all converge simultaneously are remarkably narrow. Orbital mapping by the Lunar Reconnaissance Orbiter has identified candidate building sites on ridgelines only a few hundred meters wide. On these ridgelines, the base must fit its habitats, solar arrays, thermal radiators, rover parking, construction staging areas, and eventually a nuclear reactor with its 90-meter exclusion zone. Every asset placed on the ridge competes for the same limited real estate. On Earth, you can relocate a building if the site proves suboptimal. On the Moon, every landed asset stays where it touches down. This is the environment into which NASA plans to place a permanent base, not for a 3-day visit as Apollo managed. A permanent installation required to survive thousands of thermal cycles, continuous radiation bombardment, relentless dust intrusion, and the mechanical stress of holding a breathable atmosphere inside a sealed structure on the surface of an airless world. Every astronaut who walked on the moon came back with the same warning. Not about the vacuum, not about the isolation, about the dust. Eugene Cernan, commander of Apollo 17, stated bluntly that dust was one of the most serious problems encountered on the moon. Harrison Schmitt, a geologist and the only trained scientist to walk on the surface, suffered an immediate respiratory reaction the moment regolith particles entered the cabin. Swollen nasal passages, a burning throat, clogged sinuses. He called it lunar hay fever. Every one of the 12 people who walked on the moon experienced some version of this reaction, during visits lasting between 22 and 75 hours. Brief. That is the word that should alarm anyone planning a permanent base. Lunar dust is not like any dust on Earth. Terrestrial particles are rounded and smoothed by billions of years of wind erosion, water tumbling, and chemical weathering. Lunar regolith has experienced none of these processes. Its particles are created entirely by impacts, micrometeorites slamming into the surface at speeds of tens of kilometers per second for over 4 billion years, pulverizing rock into angular, jagged fragments. Under an electron microscope, they resemble shards of broken glass rather than grains of sand. Their edges are sharp enough to cut biological tissue at the cellular level. They are also electrostatically charged, continuously bombarded by solar wind, which strips electrons from their surfaces and leaves them clinging to any material they contact with a stubbornness that mechanical brushing cannot overcome. Apollo astronauts dedicated effort to brushing dust from their suits before re-entering the lunar module. The brushing removed perhaps half the visible material. The rest clung fast. The chemical composition adds another dimension of threat. Lunar regolith is roughly 50% silicon dioxide by weight, with iron oxide and calcium oxide making up most of the remainder. The fracturing process that creates fine dust also exposes fresh mineral surfaces that have never interacted with oxygen or water. These freshly exposed surfaces are chemically reactive. When they encounter moisture, as they inevitably would inside a pressurized habitat containing human beings who breathe and sweat, they can generate free radicals, highly reactive molecular fragments that damage biological tissue. Research using lunar simulant dust has demonstrated that prolonged exposure destroys lung cells and brain cells in laboratory conditions. The particles are small enough to penetrate deep into the respiratory system, past the body's filtering mechanisms, lodging in the alveoli where gas exchange occurs. Once there, they cannot be expelled. The long-term health consequences of months or years of chronic lunar dust inhalation are genuinely unknown because no human being has ever been exposed for that duration. The existing evidence from Apollo, from simulant studies, and from analogous terrestrial exposures to fine silicate dust suggests the risk is serious, not theoretical, serious. There is no way to solve the dust problem. There are ways to manage it, but management is permanent. Every airlock cycle introduces dust into the habitat. Ventilation systems filter it continuously, using filters that themselves degrade under abrasion and must be replaced, with parts that must either be manufactured on the moon or launched from Earth. Mechanical equipment used outside accumulates dust on every moving part. Bearings grind down. Optical sensors cloud over. Electrical connectors develop resistance as dust works into contact surfaces. A dedicated dust management protocol would consume a significant portion of crew time every single day. Not occasionally, every day, for as long as the base exists. The second enemy wages war through thermal cycling. When a piece of equipment moves from sunlight into shadow at the South Pole, or when shadow sweeps across a stationary structure as the sun shifts along the horizon, the temperature changes rapidly because there is no atmospheric buffer. A surface baking at 100 degrees can begin plunging toward -100 within minutes of losing direct sunlight. Different materials expand and contract at different rates. Joints that are tight at one temperature develop gaps at another. Seals that held at 20 degrees crack at -150. Welds sound at room temperature, fracture after hundreds of cycles between extremes. At some South Pole sites, the sun dips behind nearby ridgelines and reappears abruptly, creating rapid swings between full sunlight and deep shadow. Equipment deployed there endures thousands of thermal shocks per year, each one slightly loosening joints, slightly propagating cracks, slightly degrading seals. Vacuum is the condition that makes every other problem lethal. A pressurized habitat must hold roughly 1 atmosphere of internal pressure against the external void, a pressure differential of approximately 100 kilopascals across every square meter of the habitat wall. Every airlock, every window, every cable pass-through, every equipment hatch is a penetration in that pressure envelope, a potential leak. On the ISS, one leak in the Russian Zvezda module persisted for years, requiring hundreds of cumulative crew hours to manage. On a moon base with 4 crew members, a single persistent leak of comparable difficulty could consume a quarter of all available crew time for months. In vacuum, lubricants outgas and lose their properties. Polymers become brittle under combined vacuum and radiation exposure. Metals in contact with each other can cold weld, where the absence of oxide layers in vacuum allows atomic bonds to form between touching surfaces, fusing components that were meant to move freely. This has caused mechanism failures on satellites. On a lunar base, where moving parts include airlock hinges, rover joints, drill mechanisms and construction equipment, cold welding is a persistent threat at every mechanical interface. All of these challenges converge on power, because without continuous, reliable power, nothing else functions. The habitat cannot maintain pressure, the thermal management system stops, air recycling and water processing stop. Losing power on the moon is not like losing power on Earth, where you light candles and wait for a utility truck. Losing power on the moon means losing life support. The margins are measured in hours. Even the best illuminated South Pole sites receive sunlight for approximately 80 to 90% of the lunar year. But 80 to 90% is not 100%. During shadow periods, the base must survive on stored energy or alternative power. Sustaining even 25 kilowatts through a 4-day shadow period requires approximately 2,400 kilowatt hours of stored energy. At system-level energy density, that means 16,000 kilograms of batteries, 16 metric tons of mass devoted to nothing but backup power for a single shadow period. And extreme cold reduces battery output by 30 to 50% unless the batteries themselves are heated, which consumes power from the reserves they are supposed to provide. Researchers have described lunar night survival as probably the most demanding energy storage challenge in solar system exploration. This is why NASA's plan explicitly includes nuclear power, fission reactors capable of producing continuous power through any shadow period. The technology is real and approaching readiness, but a reactor requires a radiation exclusion zone that constrains base layout, cooling radiators subject to the same dust and thermal cycling as everything else, political and regulatory approval to launch nuclear material, and backup battery capacity for contingency scenarios. Even nuclear power does not eliminate the interdependency problem. Power systems need dust management. Dust management needs power. Thermal control needs power and radiator surfaces. Radiator surfaces need dust management. Life support needs power and filtration. Filtration degrades and needs replacement parts. Every solution demands something from every other system, creating a web of interdependencies where a failure in one area cascades through all the others. Those are the surface enemies, the ones Apollo encountered in miniature during 3-day visits. Beneath them lie deeper threats that emerge only when habitation extends from days to months, from months to years. Radiation is not an event on the moon. It is a condition. An astronaut stationed on the lunar surface for 18 months would accumulate approximately 600 millisieverts of radiation exposure, approaching NASA's career limit before the tour is over. The biological consequences include elevated cancer risk, increased probability of cataracts, potential damage to the central nervous system, and cardiovascular degeneration. But galactic cosmic rays are the predictable component. The unpredictable component is far more dangerous. A major solar particle event, comparable to the August 1972 event that occurred between the Apollo 16 and Apollo 17 missions, could deliver several sieverts to an unshielded person on the lunar surface within hours. That is a lethal dose. If the Apollo 17 crew had been on the surface during that event, rather than safely on Earth, they likely would have died. A permanent base must have a radiation shelter accessible to every crew member within minutes, providing shielding equivalent to roughly 80 centimeters of lunar regolith. That means either burying the habitat underground, requiring heavy excavation equipment capable of operating in vacuum and extreme conditions, or piling hundreds of metric tons of regolith on top of a surface habitat. Both are feasible in principle, neither has been demonstrated at any scale on the lunar surface. Then there is the human body itself. The Moon's gravity is approximately 1/6 of Earth's. Not zero gravity, but partial gravity. And partial gravity is the great unknown of human space medicine. No human being has ever spent more than 3 days in 1/6 gravity. Decades of ISS research have documented what happens in near-zero gravity. Bone density decreasing at roughly 1 to 2% per month, muscle mass declining despite exercise protocols, vision degrading in a significant fraction of astronauts due to intracranial pressure changes. Whether 1/6 gravity is enough to prevent these changes is a question that can only be answered by actually putting people on the Moon for extended stays and monitoring their health. If partial gravity proves insufficient, the base must incorporate exercise equipment, providing loading equivalent to Earth gravity, possibly centrifuge-based systems, adding mass, volume, power consumption, and mechanical complexity to a habitat already strained in every category. Psychological health compounds everything. A moon-based crew would be confined to a small, pressurized volume for months, performing physically demanding and repetitive maintenance work in an environment where a single mistake can be lethal, with Earth visible only as a small disk in the sky. The isolation, confinement, monotony, and chronic danger create conditions analogous to Antarctic winter overstations and submarine deployments, both of which show documented rates of depression, interpersonal conflict, sleep disruption, and cognitive decline that increase with duration. A crew member losing bone density, accumulating radiation dose, breathing trace dust that escaped filtration, sleeping poorly from psychological stress, and spending 2 hours daily on mandatory exercise is not operating at full capacity. And the people who must maintain a complex life support system in a hostile environment are themselves being degraded by that environment. The maintenance burden builds non-linearly with time. Mechanical systems function well for the first 6 months, then begin showing wear at 9, then demand simultaneous attention across multiple systems at 12. Month 8. A dust-contaminated valve in the carbon dioxide removal system begins sticking. Replacing it takes 2 crew members 6 hours, during which time the other 2 cannot perform their scheduled EVA to clean solar panels, because the base cannot afford additional CO2 production while the primary scrubber is offline. The solar panels go uncleaned for 3 additional days. Their output drops. The following week, a secondary coolant pump shows bearing wear, likely accelerated by thermal cycling. Every choice forecloses another option. Every repair displaces another task. The maintenance backlog grows, and on the Moon, a growing maintenance backlog is not inconvenient. It is potentially lethal. The final deep threat connects everything else. Resupply fragility. A permanent moon base depends on a supply chain stretching 240,000 miles from Earth's surface to the lunar South Pole. Launching 1 kilogram of payload to the lunar surface costs between hundreds of thousands and over $1 million, depending on the vehicle. A modest resupply mission delivering a few hundred kilograms represents a $100 million operation. There is no warehouse on the Moon, no secondary supplier around the corner. If a resupply mission fails during launch or landing, which has happened to multiple lunar landers in the 2020s, the base simply receives nothing. The next opportunity may be months away. If a base requires 4 resupply missions per year to remain fully stocked, and each mission carries a 5% failure probability, the cumulative probability of experiencing at least one failure over 5 years of operations approaches 65%.